Hi guys, welcome back. Let's talk about this simple example. This is a high-speed solenoid valve, and we want to model this system. Let me walk you through the working mechanism of this system. Okay. Here you see that I have a plunger, which is connected with a push rod to a spool. Okay, and all of these connections are rigid. Yes, so there is no stiffness involved in the push rod. Inside the plunger, I have some coils, okay? And when I apply some magnetic field through the environment, actually I'm gonna make a magnetic force or electromagnetic force, okay, that pushes the plunger to the right. When the plunger goes to the right, it pushes the spool, okay, and it opens the gap here and here so that the fluid can actually pass. And also, when the plunger is basically when the electrical input is removed, then the electromagnetic force is removed, okay, and the pushback spring is gonna push the plunger and the spool and the push rod all the way back to the seated position, which is on the left side of the device. Okay, and we want to model this system using a 4-step approach. Okay, before going to model the system, you guys notice that this is in fact very crazy. Yeah, it's very difficult to model this system. Okay, and let's go and see if we can actually use our lumped system mentality and somehow simplify this model to something that we can handle. Okay, so let's go ahead and do that. What I have here is the plunger and the push rod and the spool, which are rigidly attached to each other. Yes, which means that I can probably lump the effect of all of these guys into one mass element, and I call it as my inertia element, M. Also, to make this system a little bit nicer to handle, what I can do is, instead of working with the electrical input and coil and all of these electrical stuff here, I can remove them and I can look at the effect of that electromagnetic field, which is basically an electromagnetic force, and I can include that electromagnetic force as an external force on the body of the M. The next thing is I noticed that one side of the spring here is clamped to the wall, the other side is attached to the spool. Okay, so I'm going to put a spring here, one side clamped to the wall, the other side attached to the mass. And the last thing that I'm going to work, and this is going to just be for simplification, for the purpose of simplification, is that since the spool is actually a piston-like, okay, that moves in a cylinder and actually flows in a viscous fluid here, I can somehow simplify that motion or that friction between the fluid, okay, and the piston as a damper, okay, and for the sake of simplicity, I can consider the damper as a viscous damper B, which one side of it is clamped to the wall, okay, and you see that one side of this guy is clamped to the wall, the other side is actually moving with the same velocity of the mass. Okay, now look at this. I went from this crazy representation of the system to this very simple representation of the system. Now I can talk about modeling this system. Now everything is super simple. This is a simple mass spring damper system with an external force. However, this representation was scary. Going from scary representations to simplified schematics, okay, it needs homework. It needs experience. Okay, so you need to solve many examples to be able to simplify with your lumped system mentality and go from such a crazy system to such a nice and simple representation. Regardless, let's go ahead and see how we can actually model this system. For modeling a mechanical system, the first thing that I want you guys to do is I want you guys to list the elements in the system. So all the elements that you have, I want you guys to list them. Okay? And put them in terms of inertia, stiffness, friction, the sources that you have, and the number of ODEs. Okay, let's do it together. What is my inertia element in this system? Well, it's a mechanical translation system, okay? And the only inertia element that I have is the mass m. So I'm going to write it down as m. My stiffness element in mechanical translation systems are the springs. If you look at this, I have only one spring. My friction elements in mechanical translations are my dashpot pots or the dampers. I have only one damper here. The source to this system is an external force, which I modeled as F electromagnetic. And here's the question that you need to answer. How many ODEs do you think that you would need to model this system? For now, with the let's say that with the number of inertia elements, you will have ODEs. And I'm gonna come back to this and I'm gonna slightly change this at the end of this chapter, okay? So I'm gonna say that with the number of inertia elements, I'm gonna end up with ODEs, but I'm gonna raise a flag here, okay? And I would say that, okay, at the end of this chapter, I'm gonna come back and slightly change this. Okay, now you're ready to go ahead and find that one ODE. Step one is selecting a coordinate system. Or selecting your coordinate systems. With number of independent motions, you will need coordinate systems, okay? In this problem, you see that you have only one independent motion, and that's the motion of the mass. The rest of them are basically the wall does not move, okay? So you do not need a coordinate system for the wall. Guys, note that in general, for your coordinate systems, which I'm gonna show them with CS from now on, okay, you need two things. You need a reference point or the origin, and also you need a positive direction. Okay, what's a reference point? Reference point is a point that you measure your distance or velocity from that point, okay? For instance, in this example, you can assume that the reference point is the free length of the spring. This is the origin of your coordinate system. Everything is measured from the free length of the spring. How realistic is that assumption? We don't care for now, okay? Just work with that one. And positive direction is, again, you can assume one positive direction going to the right or going to the left. It really does not matter, okay? The important thing is when you select a positive direction, you honor that positive direction for the rest of your solution. In fact, your coordinate system is your choice, and you choose it in a way that makes your life easier in the model. Okay. Step two By the way, guys, I didn't say I picked the coordinate system, started from the free length of the spring, moving to the right as the positive direction. Okay, so this is the free length of the spring. And then this is to the right. Okay. Step 2 is isolating your inertia elements. Okay. What do I mean by isolating? Look at this inertia element in the system. Okay. I mean that go ahead and grab it, disconnect it from the system. Okay. And throw it on a piece of paper. Okay. So what I'm going to do is I'm going to grab that inertia element, which is my mass, and I'm going to disconnect it from the system, and I'm going to throw it on a piece of paper. And just to make my life a little bit easier, I'm going to show my coordinate system on top of that one as well. Okay, that is isolating. The next step is step 3, which we call it as free body diagram. Okay, and I'm going to, hereafter, I'm going to show it with FBD. Okay. Looking at the free body diagram, it means that just showing the forces that are applied on your inertia element. Okay. So there is a specific order that it's a good starting point to sketch free body diagrams. Okay. And as you get experience, okay, and you'll get to know more scenarios. Okay. Then you can actually skip this order and you do what you do. Okay. But for now, let's say that the order is few CSR. What is F? F is your friction force. What is E? E is your external force. What is W? W is the weight. What is R here? R is the rope force, the force that comes from ropes. What is S here? It's your spring force. And what is C here? It is the contact force. Okay. And see, this is the order that we choose, or we pass, or we select the forces to show on the free body diagram. It minimizes our chances to make mistakes. Okay. So let's go to this free body diagram. The first force is in this few CSR is friction force. Do I have a friction element? Yes, I do have a friction element. Where is that friction element? It's here. Okay. So I need to include a friction force here instead of that friction element. Now, if you guys remember, only one side of this friction element is moving, the other side is clamped to the wall. So modeling this friction element is in fact very easy. It's going to be B multiplied by the velocity of the mass, the moving velocity. The important thing is the direction of this guy. So the magnitude is very easy. The direction of friction forces can be tricky, but for this specific problem, it's very easy because only one side of this friction element is moving, and the direction of the force of the damper is always opposing the direction of assumed motion. So if you assume that your box is actually going to the right, your friction force is always gonna oppose that direction of motion. Good. The next one is the external force. If you guys look at this, I have only one external force, and that is F electromagnetic. The direction and magnitude of that force is given to me, so I'm just going to copy it in here. The next one is the weight. Weight is always applied at the center of gravity, pointing downward. Okay. The next one is the contact force. I have a normal reaction from the surface, and that's my contact force. If you look at the wheels here, you see that I have normal reaction from the surface, okay, that they are my contact forces, okay, and I just consider the lumped effect of that as C. The next one is the spring. This one is happening here. So if you look at the spring, you see that your spring is here. Again, for this spring, it's very easy to find the magnitude of the spring force because only one end of that spring is moving. The other end is clamped to the wall. So the magnitude is Kx. This is easy. The important part is the direction of this force, whether it's going to the right or to the left. So what I want you guys to do to figure out the direction of this spring force is assume yourself as the spring. Yes? So if you are the spring and the box moves toward you to the right, are you going to be compressed or stretched? Okay. Definitely when the box goes towards you, okay, you're going to be squeezed between the box and the wall. So you're going to be compressed. Yes. When you are compressed and you want to get rid of that compression, you are going to push back. Yes. So if you push back, you're going to force the spring on this direction. Yes. You're going to push it back on these two directions. And that's exactly what's happening to that spring. So when you are dealing with the spring elements, I need you guys to close your eyes, imagine that you are the spring, figure out if you're squeezed or stretched, okay, and from that position, okay, figure out what's the direction of that forces. Whereas in the friction elements, it's a little bit easier, okay, since they are always applied opposite direction of motion. If you are going to the right, they're going to apply to the left. If you are going to go to the left, they are applied to the right. Okay. And the next force here in this sequence of few CSR is the rope force. Unfortunately, we do not have any rope in this problem, so we are done with the free body diagram. Guys, note that step 3 is the heart of your solution. Okay, and we're going to talk about this step a little bit more. As an engineer, you are expected to draw flawless free body diagrams. This is one thing that people are asking you to do. The other thing is, look at this free body diagram and the motion of the box. If you look at this, you see that the box has no upright motion. Yes, there are no vertical motion on this direction. The only motion that we have is a horizontal motion, which means that the vertical motion is actually a static motion. There is no acceleration. Okay. And since there is no acceleration, it's very boring and very simple. You can say that, okay, W is in fact equals to C. Since you do not have any motion on the vertical direction, you can somehow simplify the free body diagram, okay, and get rid of the forces on the vertical direction. Okay. Because they are not going to play any role in the problem. Okay. So with that, from now on, whenever we do not have a motion on a specific direction, I'm going to neglect that direction altogether. Okay? And the forces that are applied actually in that direction. Since my free body diagram is complete, I can go safely to step 4, which is equation of motion. Okay. For the equation of motion, I'm going to write down the Newton's second law for each of the isolated mass bodies. Okay. So I have one mass or isolated mass. So I would say summation of forces along x equals to mx double dot. This is my equation of motion. This is Newton's second law. There's nothing new about this. Yes. Look at this. I have 1, 2, and 3 forces applied on this body. And it happened that force 1, which is the electromagnetic force, is in the same direction x of my body, of my coordinate system. So this is positive. And force 2 and 3 are actually applied on the opposite direction of x, if you look at this, and they are negative. Yes? So let's go ahead and write them. Positive F electromagnetic minus negative Bx dot minus Kx equals to Mx double dot. You're not done yet. There is one important thing to do. Keep the inputs on one side or the sources on one side. Bring all the dynamic terms to the other side. So my input is FEM or F electromagnetic. I'll keep it on one side and bring all the other terms on to the other side. So it's going to be FEM equals to M x double dot plus B x dot plus Kx. Good? Okay. Now look at this. There's one important test that I need to do before I box this equation. Okay, so this is actually a sanity test. Okay. And for this sanity test, I would identify the families of dynamic variables. Okay, and see whether within a family I have different sign changes between the members or not. Okay, so look at the right hand side of this equation. You see that I have family of x and its derivatives. Yes, so family of x is what I'm dealing with on this equation, in this equation. And I have 3 members of that family, x, x dot, and x double dot. They all belong to the family of x, okay? And they're the 3 members of that family. Now look at this. This is a positive sign, mass is positive, positive, and positive. There are no sign changes within the member of the families, within the family, among the members of the family. Yes? So I can go ahead and safely box this equation. If there was a sign change among the members of this family, then I would be in trouble. I would go and first check my equation of motion, then check my free body diagram to see if I made a mistake here or there. Okay. For this, everything is working out. So basically, this is your final solution. Okay. And this is the equation for the mass spring damper system.